Hello there and welcome back to the Science Sleepy Minds. You're hovering above a vast ancient landscape. Below you, the Earth is whole, a single, enormous supercontinent called Pangaea, stitched together like a jigsaw puzzle no one dares to break. But it's warm here, and not just because the air is thick with volcanic breath. The crust beneath your feet, it's not settled. You can almost feel the pressure building. Something is about to give. And let's be clear, you probably won't survive this. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're listening from and what time it is there. I love seeing how far this little community drifts. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You walk barefoot across what is now central Pangaea. The land stretches endlessly in all directions, a single continent wrapping halfway around the globe. There's no Atlantic Ocean, no familiar curve of Africa against South America, just forests, deserts, swamps, and stillness. But not for long. Deep below the surface, the mantle churns. It's a slow-motion soup of molten rock and mineral slush, convecting in looping patterns that make the crust above bulge and crack. You wouldn't feel it. Not yet. But this supercontinent, it's doomed, because Earth hates staying still. Pangaea began forming around 335 million years ago, give or take a few rock layers. By 175 million years ago, it had started to break apart, quietly at first. A rift here, a thinning crust there, kind of like when the first seam of a loaf of bread splits in the oven. You notice it too late to do anything about it, and then, well, it's too far gone. You stroll through what will someday be Morocco, but the air smells vaguely Appalachian, because these mountain ranges, yes, even the Blue Ridge, were once part of the same colossal smash. When continents collide, they crumple like fender benders. The Appalachians are the scar tissue of an ancient slam between North America and Africa. Historians still argue whether that early collision truly began Pangaea's formation, or merely sped it along. Now, as you look around, it's hard to believe this was once Earth's version of a group hug, but you can already see where the hugs are loosening. Rifts have opened, like hairline cracks in a windshield. You follow one that's quietly tugging what will be South America away from what will be Africa. And yes, the split starts in earnest underwater. The Tethys Sea, a warm inland ocean with coral reefs and creepy early squids, will eventually become the Mediterranean. Right now, it's just lapping gently at the edges of a stressed-out crust. The process of breaking apart takes tens of millions of years. But for you, in this dreamlike drift through geological time, it feels oddly fast. 1 minute you're standing on a unified continent, and the next, whoosh, oceans appear, land shifts. That tree you saw earlier, now it's on a different plate entirely. Rude. Now let's talk fashion. The dinosaurs of this era are in full stride. Stegosaurus wanders through conifer forests. Sauropods wade through ancient river deltas, totally unaware that the continents beneath them are splitting faster than some friendships on group vacations. You pause to sit near the proto-Atlantic, newly forming. No real waves yet, just a crack widening, millimetre by millimetre, century by century. Lava oozes gently from rift valleys, cooling into basalt. Eventually, this newborn ocean will push the Americas westward, all because the Earth below is always reheating and respreading itself. The quirky bit: ancient Pangaea wasn't the first time Earth decided to bundle up. Before it, there were other supercontinents: Rodinia, Columbia, Kenneland, each with their own slightly dramatic story arcs of coming together, splitting apart and ghosting one another. And just like in your favourite slow burn series, this plot repeats. Historians still debate whether these cycles follow a set rhythm or are just really chaotic roommate dynamics on a planetary scale. The breakup of Pangaea is the most recent we understand in detail, and it reshaped everything: climate, ocean currents, life evolution. The continents didn't just drift, they wandered into new weather systems, crashed into strangers, and in some cases started fights with volcanoes. Speaking of wandering, you float now above what will become the eastern seaboard of North America. It looks nothing like it does today. No skyscrapers, no boardwalks, just thick forests and early mammals scurrying underfoot trying to stay out of dinosaur jaws. And all around you, invisible, are the fingerprints of drift. Fossils of the same freshwater reptiles, Mesosaurus, if you're collecting trivia points, show up on both sides of the Atlantic. Ancient glacial scars in Africa line up eerily with similar patterns in South America. You start to see the logic behind the theory and the wonder. For centuries, people had no idea the ground beneath them moved. The idea of continents drifting seemed absurd, like suggesting your house might quietly wander off while you're asleep. But in the early 20th century, a German meteorologist named Alfred Wegener had the audacity to say, "Yeah, actually, I think they do." He noticed the matching coastlines, the shared fossils, the geological scars, and he coined the term continental drift. People laughed. Seriously, the idea was dismissed for decades. Historians still argue whether Wegener's lack of a mechanism, the how, was what doomed him, or whether the scientific community just wasn't ready to admit the Earth was that squishy. Now, of course, we know Wegener was right. Mostly. The continents do drift, but they're just the passengers. The plates are the real vehicles, and those plates ride atop the molten dance party deep below, sliding, colliding and subducting like they've got somewhere to be. You drift upward now, into the clouds, looking down at the baby Atlantic. It'll grow into a vast ocean someday, complete with sunken ships, dolphins and questionable cruise ship karaoke. But right now, it's just a crack. A slow, widening breath in Earth's long exhale, and as the continents separate, life adapts. Ecosystems split. New species evolve in isolation. Evolution doesn't take sides. It just keeps going, reshaping life like tectonics reshape land. You realize lying there that this story, Pangaea's long goodbye, isn't just about geology. It's about inevitability, about slow change that no one notices until it's already too late, about how you're always moving, even when you feel completely still. And that perhaps is the quiet miracle of plate tectonics. You don't need to feel it for it to be real. You're sinking now, down through soil, bedrock, and into the glowing layers of Earth that few ever think about, unless they've taken an unfortunate tumble into a very dramatic volcano. The temperature climbs, the pressure hugs tighter, and the light around you shifts from orange to a deep, pulsing red. You've left the crust behind, and you're drifting inside the mantle, the part of Earth responsible for every drifting continent, quaking fault, and inconveniently placed mountain range. The mantle isn't liquid like some giant lava lamp. It's more like hot, slow-moving caramel. Solid, yes, but ductile over long timescales. Here, convection currents churn constantly. Hotter material rises, cooler material sinks, and the process repeats endlessly, like an overachieving pot of stew. This is Earth's inner engine, and it's been humming for over 4 billion years without a single oil change. Everywhere around you, mineral grains realign under pressure. Tiny crystals deform and then rebound. The effect is hypnotic, like watching honey fold itself into patterns it never trained for. These flows are what drag the tectonic plates above, inch by inch across the planet's surface. You're floating in the gears of a planetary machine. Of course, you'll remember that the crust above you isn't some pristine, unbroken skin. It's shattered into massive puzzle pieces, 7 major tectonic plates and a bunch of smaller, feisty ones that act like they're more important than they are. Each plate rests on this slowly churning mantle, and each one moves at a different speed and direction. It's like bumper cars, but over millions of years and with fewer joyful screams. Historians still argue whether mantle plumes, those vertical jets of superheated rock, are shaped like narrow columns or wide blobs, and if they rise from the outer core or just the lower mantle. Either way, they're like giant cosmic stovetops that help drive tectonic chaos. Sit long enough above one and you get Hawaii. Sit a little too long and you get a super volcano. One of the wildest things about this engine room is how little we actually know about it. Sure, we've got seismic readings, lab experiments, computer models, but nobody's ever drilled even a fraction of the way into the mantle, let alone the core. Your ride tonight is the only express pass into this realm that doesn't come with a side of death. Now close your eyes, if you haven't already, and imagine you're part of the flow. You're heat rising from the core mantle boundary. You're a ribbon of peridotite, twisted and heated and pushed upward into the asthenosphere, just beneath the lithosphere where plates begin to drag. You're not rushing, you've got time, millions of years of it. A quirky tidbit. In the 1970s, scientists seriously proposed detonating nuclear bombs deep underground to try to reach the mantle, in a project charmingly dubbed Project Mahal. It was scrapped due to costs, technical difficulties, and probably the unspoken realization that blowing up Earth to understand it is a bit like smashing your phone to find the battery. Noble effort though. As you continue to drift through this thick glowing sea, you notice something odd. Despite the incredible pressure, millions of times what you'd feel at sea level, Earth isn't imploding. The core's heat keeps it buoyant, balanced, alive in its slow churn. And that heat? It comes from radioactive decay, uranium, thorium, potassium-40, breaking down and releasing warmth like an ancient stove nobody turned off. This is one of those times where you realise Earth is very much not a dead rock. It's alive with motion, humming with internal heat and constantly adjusting itself like a restless sleeper. The surface may look peaceful, but down here, it's never still. Now picture a single plate above you. Let's say the Pacific Plate, the largest of them all. It's so big it could comfortably hold all the continents in one giant geologic buffet. It's riding atop the mantle's convection like a surfboard, only the wave is 1,000 kilometers wide and moves at the speed of your fingernail growing. But don't laugh. That fingernail speed drift is powerful enough to open oceans, form island chains, and ruin city planning with one good quake. Some plates are diverging, moving apart, pulled by upwelling currents. Others are converging, smashing together over descending plumes. And some just slide past each other awkwardly, like X's forced to share a sidewalk. The direction and style of each movement are dictated by the deep mantle beneath, which means that the continents you see on the surface are just riding the whims of what's cooking below. You feel a subtle pulse, a ripple through the mantle. That's an earthquake far above, its shockwave racing down through the earth like a sound check. You can't hear it, but you can feel the resonance. Another reminder that the surface might shake, but it's the interior that calls the shots. Up above, people are going about their lives, building cities, setting up lawn chairs, arguing on the internet. All while beneath them, this enormous unseen engine is quietly dragging their land masses in new directions. And no, they don't get a say in the route. You rise slowly now, back toward the lithosphere, the crust plus the brittle uppermost mantle. That's the layer tectonic plates are made of. The one you live on, the one that breaks, bends, uplifts, and sinks. It's a funny thing. The very concept of solid ground is, geologically speaking, a lie. You live on floating fragments of crust that are rafting across a gooey, heat-pumping sea of silicates and metals. Your whole reality is just a ride on a rocky barge with no brakes and no destination, just endless drift. And while the plates move in measurable ways today, they didn't always. Back in Earth's youth, say 3 to 4 billion years ago, the mantle was way hotter, and plates may not have even existed in their current form. Historians still argue whether plate tectonics began early in Earth's history, or only kicked off once the mantle cooled and the crust could actually fracture. Either way, what you're walking on now is the product of billions of years of internal combustion. Slow, dangerous, majestic combustion. You break through the crust again, emerging in the moonlit silence of a desert plateau. The ground beneath you hums with slow power, but the surface seems still. You know better now. The continents move, the crust breaks, the mantle breathes, and you, tiny passenger of this planet, are never truly at rest. You're back above ground now, tracing the surface of a world that only pretends to be still. From above, Earth seems serene. Oceans tucked into their basins, continents lazily stretched out under clouds. But you've seen what lies beneath, and now you start to notice the cracks. You walk along the dry spine of a desert valley, and beneath your feet something doesn't quite fit. It's subtle, like a bad tile job. The land is divided, not in smooth curves, but in jagged, interlocking blocks. You've reached the broken shell of our planet. The crust is not okay. Earth's outermost layer is thin, laughably thin, really. If Earth were a peach, the crust would be the fuzz. That's it. And yet, it's where everything you've ever known lives. Cities, forests, dogs, ice cream, regret. All of it on a layer that's rarely thicker than 40 kilometers, and often much less. The crust is divided into tectonic plates, and these plates are massive. They can span entire oceans, cross continents, and crash into each other with a slow-motion violence you don't feel until it's way too late. You're standing on one right now, probably the North American plate, unless you've somehow wandered to, say, the Nazca plate while sleepwalking. The plates are made of two types of crust. continental and oceanic. Continental crust is thick and old, really old, with parts dating back over 4 billion years. It's also lighter, which is why it floats higher. Oceanic crust, on the other hand, is thinner, denser, and younger. It's born hot at mid-ocean ridges and sinks back into the mantle like a responsible party guest cleaning up after itself. And here's the twist. These plates are moving. Not metaphorically, not emotionally. Physically moving, just very slowly. On average, a plate shifts about as fast as your fingernails grow, 1 to 10 centimeters per year. You won't feel it in your lifetime, but geologically speaking, it's practically sprinting. You kneel by a fissure, an actual boundary between plates. It doesn't look like much. A few rocks pushed up. Maybe a tiny rift you could step over. But this is where continents fracture, where earthquakes begin, where the crust literally can't hold itself together anymore. One historical gem for you. In 1906, the San Francisco earthquake tore through California with enough force to shift land horizontally by several meters in less than a minute. The shaking destroyed nearly 80% of the city. Historians still argue whether it was the quake itself or the fires afterward that did more damage, but either way, the crust was the first to crack. It's strange, really, this idea that something so colossal could be so fragile. But that's the truth of plate tectonics. Earth's crust isn't one smooth shell. It's shattered, compromised, always on edge. Now look closer. The boundaries between these plates come in different flavors. Some spread apart, others crash together, still others slide past each other with the passive-aggressive grace of rival co-workers at an office potluck. These are the 3 primary types of plate boundaries: divergent, convergent, and transform. You'll get cozy with each soon enough, but for now, let's hang out where 2 plates are gently pulling apart. Like friends who said, "We'll stay in touch," and then didn't. This is a divergent boundary, and it's often found at mid-ocean ridges, where molten rock rises from below and pushes the plates in opposite directions. It also happens on land, like the East African Rift, where the continent is literally stretching itself in half. You could sit in a lawn chair there and very, very slowly watch 2 future continents form. Quirky side note, Iceland is the only country where you can walk between 2 diverging plates. The mid-Atlantic ridge surfaces right there, and tourists flock to straddle the North American and Eurasian plates like it's a geological selfie station. One step here, and you're technically continental hopping. As you stroll on, the landscape shifts. Now you're in a transformed boundary zone. Think the San Andreas Fault. 2 plates are scraping past one another, not kindly. The stress builds over decades or centuries, and then suddenly, snap. Earthquakes. The kind that knock books off shelves and send late-night texts to seismologists. Transformed boundaries are messy. No crust gets created or destroyed. It's just side-to-side grinding, which sounds harmless, until you realise the amount of pressure involved. It's like trying to drag 2 giant slabs of rough concrete past one another while they scream internally. You find a quiet spot now, somewhere remote. Maybe in the ocean, maybe in a desert. Somewhere where the crust feels stable, but it isn't. Because intraplate earthquakes exist too. These are the jump scares of geology. They happen far from plate boundaries and remind us that even the middle of a plate isn't immune to stress. The 1811 to 1812 New Madrid earthquakes in the central US were some of the most powerful in North American history, and they struck the middle of a plate, nowhere near a boundary. Scientists still debate the cause. Historians still argue whether such quakes are relics of ancient rift zones, or caused by subtle shifts in the crust's integrity. Either way, it's a nice reminder that no place is perfectly still. You crouch again and press your hand to the rock. It's warm, a little rough, and deeply tired. This planet has been building and breaking itself for eons. The crust isn't smooth because it's not supposed to be. It's a battlefield, a mosaic, a memory map of everything that's ever collided, split, risen, or sunk. And you? You're standing on one of the fragments. The next time someone says solid as the earth, you'll know better. You'll smile just a little and think about the heat below, the fractures beneath your town, and the continent still playing slow-motion bumper cars under your bed. The crust is not okay, and somehow that makes it even more amazing. The air gets cooler as you drift westward, until the horizon shimmers with salt spray and silver blue nothing. Before you, the ocean spreads out like an endless sheet of wrinkled glass. But don't be fooled by the calm, something enormous is happening under there. Beneath those gentle waves, Earth is manufacturing brand new crust in real time. Welcome to the mid-ocean ridge, where molten rock oozes from deep within the mantle and hardens into fresh sea floor like a never-ending loaf of geological bread. It's one of the most productive environments on Earth, and yet you probably couldn't point to one on a map. This is the ocean floor conveyor belt, and it is constantly, relentlessly remaking the planet. You float down, past curious schools of fish and the occasional confused squid, toward a ridge that rises like a spine from the seafloor. It's not just one mountain range, it's the largest mountain chain on Earth, wrapping around the globe like a belt made of volcanic ambition. The Mid-Atlantic Ridge alone stretches over 16,000 kilometers, and yet it's mostly invisible, drowned under thousands of meters of cold seawater. Here, divergent plates do their slow, awkward dance. The oceanic plates on either side of the ridge are moving apart, and as they do, magma wells up from below to fill the gap. It cools, hardens, and becomes brand new crust. No fanfare, no ribbon cutting, just a slow, constant birth of Earth's skin. You reach down and touch the basalt. It's still warm, freshly made, less than a few hours old if you want to believe in the magic of deep time moving faster for a moment. Over millions of years, this new crust will be carried away from the ridge like luggage on a very delayed baggage carousel. Eventually it will sink back into the mantle somewhere far away, but for now, it's new, it's sharp, it's yours. This process is called seafloor spreading, and it was one of the final puzzle pieces that convinced scientists that plate tectonics wasn't just a theory, it was how Earth worked. In the 1960s, researchers discovered symmetrical magnetic stripes on either side of mid-ocean ridges, each one a frozen record of Earth's magnetic field at the time the rock cooled. When the field flipped direction, so did the magnetism in the new crust. It was like finding a barcode etched into the Earth. A quirky little aside, Earth's magnetic field doesn't just flip occasionally, it does so randomly. Sometimes thousands of years pass between reversals, sometimes millions. Historians still argue whether these flips are triggered by changes in the outer core or if the core's just moody. But the record in the ocean floor doesn't lie. You're walking over stripes of history. Back in the present moment, you notice small chimneys along the ridge, hydrothermal vents, often called black smokers. Superheated water, rich in minerals, bursts from the seafloor like underwater geysers. Around them, life blooms in ways that should be impossible. Giant tube worms, blind crabs, and heat-loving microbes that couldn't care less about sunlight. This is one of the few places on Earth where life exists independently of the sun. These organisms thrive on chemosynthesis, converting chemicals from the vents into energy. It's like life hacked the rules and decided, nah, photosynthesis is optional. That discovery blew open theories about where life could exist, not just on Earth, but maybe on icy moons like Europa or Enceladus. As you wander farther from the ridge, the crust beneath you grows older, colder, and thicker. Just like people, oceanic crust matures and eventually slows down. It sags under its own weight, gathering sediment and growing tired. Eventually it will meet its end in a trench far, far away, but we'll get to that soon. For now, let's take a moment to appreciate the absurd scale of this process. Since you started listening to this section, Earth has created several square meters of new crust. That's right. Even while you sleep, the planet is pulling itself apart and patching itself back together like some sleep-deprived patchwork quilt, and yet, it's slow. Painfully slow. You could sit in a submersible for your entire life and not see more than a few centimeters of movement, but scale out and it's profound. The Atlantic Ocean, for instance, is growing wider by about 2.5 centimeters per year. That's roughly the speed your fingernails grow. At that rate, the Atlantic has expanded from a newborn crack into a full-blown ocean in about 180 million years. And it's still going. Historians still debate what triggered the initial rifting between Africa and the Americas. Some blame mantle plumes. Others suggest complex feedback between crustal tension and deep thermal currents. Either way, the result was this vast widening scar, the Atlantic, and the slow ballet of continents parting ways. Of course, this conveyor belt only works if there's somewhere for the crust to go. You can't keep making new crust forever without running out of room. Which is why, on the other side of the planet, plates are being swallowed again in deep, hungry trenches, recycling at its most dramatic. But we'll save that delightful descent for later. For now, Imagine zooming out. See the ridge as a glowing seam on a planetary baseball. Watch the crust peel away from it in both directions, toward Africa, toward the Americas. It's a slow, stubborn unravelling, and through it all, Earth's engine just keeps humming. A fun but slightly alarming fact: most of the volcanic activity on Earth doesn't happen on land. It happens here, along the mid-ocean ridges, in silence and darkness. You don't see it, you don't feel it, but it's reshaping the world, one breath of magma at a time, and you, lucky drifter, have seen it for yourself. So as you rise back through the water, past the lazy swirl of bioluminescent jellyfish and ancient submarine cables, you carry this secret knowledge. The ocean floor is not flat, not still, and not old. It's a living belt, endlessly making new Earth and sending it off into the world like crusty little postcards from the deep. The continents may drift slowly, but this is where the story begins. Again and again. You're hovering now over a place where the ocean floor takes a sudden, impossible plunge. The sunlight vanishes, the pressure builds, and the temperature drops like a stone. You found yourself above a deep ocean trench, the kind that swallows up entire tectonic plates without so much as a polite burp. This is subduction, and it is one of the most dramatic moves Earth makes. If seafloor spreading is Earth's creative side, subduction is its inner minimalist. Out with the old, in with the new. Oceanic crust, dragged for millions of years away from its birthplace at the mid-ocean ridge, eventually runs out of room and time. When it reaches a continental margin or another oceanic plate, it dives beneath it. Slowly and with much resistance, the plate sinks into the mantle, its crustal reincarnation. Except there's fire involved. A lot of fire. You lean forward and peer into the Mariana Trench, Earth's deepest known point. The Pacific Plate is diving beneath the smaller Mariana Plate here, creating a gash in the seafloor nearly 11 kilometers deep. That's deeper than Mount Everest is tall, it's dark, it's cold, and yet even here life clings on. Ghostly amphipods, alien-looking fish, and one very confused plastic bag that somehow made it down this far. Yes, that really happened. This is no gentle glide. The descending plate grinds and warps as it goes. Pressure and heat build up along the boundary, and the crust begins to dehydrate, literally squeezing out water trapped in its minerals. This water rises into the overlying mantle wedge, lowering its melting point. Result? Volcanoes, lots of them. In fact, most of the world's volcanic arcs, like the Andes, the Cascades, and Japan's mountainous spine, exist because of subduction. As the plate dives, it not only melts but feeds magma upward into the crust above. The surface seems quiet, even peaceful at times, but underneath it's a bubbling cauldron of geological mischief. Let's take a quick stroll up the Andes. You're standing now in Peru, one foot on the South American plate, the other floating above the Nazca Plate as it sinks below. The Andes have been growing here for tens of millions of years thanks to this relentless collision. Each tremor, each eruption, each mountain inch gained. That's subduction doing its day job. A quirky twist. Sometimes, the descending plate doesn't go quietly. It can jam, crack, or even flatten out, causing the mountains above to deform in weird, unpredictable ways. Historians still argue whether these flat subduction zones are caused by irregular plate angles, buoyant crustal segments, or simply a crust that refuses to behave. Either way, the result can be catastrophic, like the 1960 Great Chilean Earthquake, the most powerful quake ever recorded at a magnitude of 9.5. That monster quake was born from a stuck subduction zone finally letting go. You walk now along the Japan Trench, where the Pacific Plate is sliding beneath the Okhotsk Plate, which is part of the larger North American Plate. Yes, that one stretches far. This is where the 2011 Tohoku earthquake erupted from the deep, unleashing a massive tsunami and shaking the Earth's axis by several centimeters. The event was a devastating reminder that these boundaries are anything but theoretical. Subduction isn't a smooth process. The plates don't want to dive, they resist, and the energy stored during this standoff eventually snaps free as a megathrust earthquake. When it does, the seafloor can heave upward by meters in seconds, pushing a wall of water ahead of it. That's how tsunamis happen, not from some weather fluke, but from continents suddenly jerking upward like startled cats. And beneath it all, the descending slab continues. It can sink hundreds of kilometers into the mantle, visible to seismologists as cold, dense slabs in tomographic images, ghost trails of vanished crust slowly being absorbed. Some researchers believe these subducted plates may accumulate near the core mantle boundary, forming a kind of graveyard layer. Others suggest they mix and melt long before they ever make it that far. Historians still argue whether slabs ever truly disappear, or if their chemistry permanently alters the deep mantle over time, creating hotspots and future volcanic upwellings. It's an ongoing conversation, mostly carried out in dense scientific journals and overly long conference panels. Meanwhile, you continue your descent, only this time metaphorically, into the implications of subduction. This process doesn't just recycle crust, it drives continental drift, triggers mountain building, ignites volcanic arcs, and sets the stage for devastating earthquakes. It literally reshapes the map. And yes, it's still happening today. Subduction zones rim the Pacific Ocean, forming what's known as the Ring of Fire. This horseshoe of plate boundaries is home to over 75% of the world's active volcanoes and some of its most densely populated regions. It's like building your house on a conveyor belt that occasionally explodes. But hey, the view's nice. One more twist before we climb out of the trench. Not all subduction is created equal. Oceanic subduction creates island arcs like the Aleutians or the Philippines. Oceanic continental subduction builds volcanic mountain ranges like the Andes, and continental collisions. Well, those are a whole different party, and we're headed there next. For now, you're rising again, past the crust that's melting, the pressure zones that still tremble, and the slow curve of a slab disappearing into the deep. Subduction is violent, yes, but it's also essential. It balances the books, it closes the crustal loop, and every time a plate dives into the trench, Earth whispers a gentle tectonic thank you. So next time you hear about an earthquake or a volcano on the news, you'll know what's really happening. The planet, as always, cleaning up after itself. The air is thinner here. You've climbed so high that your ears pop and the wind tastes like ice. You're standing in the shadows of jagged giants, the Himalayas, the rooftop of the world. But these mountains aren't just impressive. They're active, rising still. You're standing in the aftermath of an epic tectonic collision, one that's not even close to finished. Right here, the Indian plate has crashed into the Eurasian plate, and neither is willing to back down. The result? An ongoing continental standoff that's shoving crust upward in slow, crumpled folds like a rug bunched against a wall. This is what happens when continents collide. You don't get subduction. You get elevation. You get mountain time. Unlike oceanic crust, which happily sinks under its denser cousin, continental crust is too buoyant to dive. So when two continents meet, they just smash. They thicken. They compress. They wrinkle into ranges so massive they affect global weather patterns. And the Himalayas? They're the poster children of this process, a towering reminder that plates aren't polite, they're persistent. It all began around 50 million years ago, when India, once part of the ancient southern continent Gondwana, started drifting north across the Tethys Ocean. India was fast, geologically speaking anyway, zipping along at about 15 to 20 centimetres per year, which is tectonic speed demon territory. You might remember from earlier, most plates crawl at a few centimetres a year. India was in a hurry. Historians still argue whether that rapid motion was due to unusual mantle dynamics, or if it just had somewhere very important to be. When India hit Eurasia, it didn't stop. It couldn't. The impact crumpled the crust like a slow-motion car crash, sending rock upward into folded peaks and deep into the Earth's mantle. That crash, by the way, is still happening. India continues to push north, and the Himalayas continue to rise at about 5 millimeters per year. It's like watching molasses pile up, painfully slow until you realize it's moving entire continents. You sit for a moment on a rocky ledge. Below you, prayer flags flap in the wind. Yaks wander trails that twist across these seismic scars. It feels ancient, eternal, but it's not. The Himalayas are young, geologically speaking. Everest, towering at nearly 9,000 meters, is still rising, and one day it might be taller, or gone. Mountains rise, and eventually they erode. You might think mountains are all about peaks and valleys, but beneath them lies something even more important: roots. Like icebergs, mountains have deep, thick foundations of crust that extend downward. When plates collide, the crust thickens, forming these hidden roots that help keep the range from collapsing under its own weight. But these roots don't just sit there. They insulate, they press, They even melt. In some cases, crustal melting at these depths feeds magmatic intrusions, giant underground blobs of granite that will, one day, surface as sparkling outcrops for tourists to photograph and geologists to nerd out over. Let's not forget the earthquakes. Oh yes, when continents collide, the tension doesn't just fold rock, it fractures it. The Indian-Eurasian collision zone is one of the most seismically active regions on Earth. The 2015 Nepal earthquake, for instance, was the direct result of this relentless compression. The quake killed thousands and shifted parts of Kathmandu by several meters in mere seconds. That's the thing about continental collisions, they're slow until they're not. A quirky tidbit. Some researchers believe that the rise of the Himalayas might have helped cool the planet. As the mountains grew, chemical weathering of exposed rock may have pulled carbon dioxide from the atmosphere, gradually reducing greenhouse gases and contributing to long-term global cooling. Mountains, it turns out, may be accidental climate regulators, and this isn't the only place where plates have butted heads to build something big. The Alps, the Zagros Mountains, the Appalachians, all born from collisions, each with their own timeline, personality and erosion scars. The Appalachians, for example, were once Himalaya-sized, raised high during the collision between North America and Africa when Pangaea was forming. Now they're old, rounded and gentle, like a retired heavyweight champ, still solid but no longer in the fight. Historians still argue whether these ancient mountain ranges formed in single collisions or in complex cycles of crashing and retreating. The evidence is buried in twisted metamorphic rocks, crumpled like geological receipts for every tectonic argument Earth has ever had. You move now through the Tibetan Plateau, the world's largest and highest. It's not just mountains here, it's an entire elevated continent. Formed by the same collision, this uplifted region spans over 2.5 million square kilometers. It's so high it affects the jet stream and the monsoon systems of South Asia. A continental crash doesn't just build a mountain, it reshapes the sky. You wonder, what happens when the plates finally stop? When India's push slows, and the Himalayas crumble back to sea level under the steady hand of erosion? Will another continent rise to take its place? Will another ocean close? Spoiler alert, yes. Given time, everything moves. But for now, the crust here is still crumpling, still rising. You can feel it in the rocks underfoot, layered, twisted, compacted like pages of an ancient book pressed too tightly together. So next time someone mentions plate tectonics, remember this. It's not just about drifting continents. Sometimes, it's about the quiet violence of two immovable objects trying to share the same space. And when they do, the world gets taller, you feel it before you see it. A low rumble in the pit of your stomach, a warmth that creeps through the soles of your feet. Then a faint orange glow begins to rise over the horizon, flickering against the night sky like a warning flare from the planet itself. You've arrived at one of Earth's most volatile features, the volcano. Volcanoes are Earth's pressure valves, quietly, or not so quietly, venting heat, gas, and molten rock from deep within. Without them, the planet would crack under its own internal stress. But with them, you get fireworks, you get chaos, you get some of the most fertile soil and dangerous real estate on Earth. You're floating above the ring of fire, the seismically supercharged loop that wraps around the Pacific Ocean like a necklace of ticking time bombs. It holds over 75% of the world's active volcanoes, and none of them are here to play. Your first stop is Mount Fuji, rising with almost absurd elegance from the Japanese countryside. It's the kind of volcano that makes you forget it's actually dangerous, until it isn't. Fuji sits atop a messy tectonic triple date, where the Pacific Plate, the Philippine Sea Plate, and the Eurasian Plate all interact. It's a recipe for both earthquakes and eruptions, and Japan lives constantly with both. Volcanoes form in a few different ways, but subduction zones like this are among the most dramatic. Remember from our time in the trenches, as an oceanic plate dives beneath a continental one, it melts, releasing gases and magma that bubble up like a bad idea in a group chat. The crust above doesn't always cooperate. Sometimes it lets off steam slowly. Other times, it explodes with enough force to rewrite the landscape. You now drift toward Mount St. Helens, where in 1980, an eruption blew the mountain's entire north face sideways in one of the most powerful geological tantrums in North American history. Ash rained down across multiple states, trees flattened like matchsticks, and the crater left behind looked like Earth had taken a bite out of itself. The quirky detail? Before that eruption, the mountain bulged. Not metaphorically, physically. A growing mound appeared on the north side, pushed up by magma. Scientists watched it nervously, but even then, the sheer force of the blast shocked everyone. Historians still argue whether warning signs like gas emissions and seismic tremors are enough to predict an eruption, or if volcanoes simply refuse to follow our human timelines. Volcanoes aren't just land-based, of course. Some of the most active volcanic activity happens underwater, along mid-ocean ridges and hotspots. We've seen a few already. But here's something deliciously dramatic. The largest volcano on Earth isn't what most people picture. It's called Tamu Massif, and it's hiding beneath the Pacific Ocean. It covers an area roughly the size of New Mexico. Bet you didn't see that one coming. Then there are the supervolcanoes, a class of eruptions so large they don't even bother with traditional cone shapes. They explode from massive underground chambers, causing continent-scale disasters. Yellowstone is one of these. Don't worry, it's not erupting anytime soon. Probably. Maybe. Scientists monitor it closely, but even with all our tech, predicting a super eruption is like trying to guess when your cat will knock over that expensive lamp. Now let's talk lava. Not all lava is the same. Some is basaltic, smooth and runny, like the kind in Hawaii that flows gracefully and photogenically, until it isn't. Other lava is andesitic or rhyolitic, thicker, gassier, and far more likely to explode. If basaltic lava is a lazy river, rhyolitic lava is a shaken soda can in the back of a car on a bumpy road. You walk now across the cooled remnants of a lava field, sharp, black and steaming in places. Life is already creeping back. Ferns grow in cracks, birds nest in the warmth. It's a strange balance. Destruction gives way to creation. Volcanic soils, rich in minerals, are among the most fertile on Earth. Civilizations have always settled near volcanoes despite the risk, drawn in by the land and trapped by the danger. A quick history lesson. Pompeii, 79 CE. The residents of this Roman town lived in the shadow of Mount Vesuvius, unaware that the mountain could still erupt. When it did, the result was fast, brutal, and eerily well preserved. Ash buried the city so quickly that loaves of bread were found still in ovens, and body casts still show people frozen mid-motion. It was one of the earliest historical wake-up calls that volcanoes don't sleep peacefully forever, and yet people keep returning. To Naples, to Kilauea, to Merope. The lure of volcanoes is part danger, part awe, part deep geological memory. The Earth breathes through these fiery holes, and sometimes we're just too curious to stay away. Historians still argue whether some ancient myths, like Atlantis or the fiery underworlds of various cultures, were inspired by volcanic eruptions. It's entirely possible. After all, what else could explain entire cities vanishing, land cracking open, fire pouring from the earth? Even today, the imagery is hard to forget. You close your eyes and listen now to the mountain's breath. A low hiss of escaping gas, a faint tremor in the rock, maybe nothing, maybe everything. That's the problem with volcanoes. They keep their secrets close. You rise again, drifting over a line of volcanoes stretching down through the Cascades, then around the edge of the Pacific to Indonesia, where entire chains of islands exist purely because volcanoes built them. You're flying above layers of crust formed by lava, ash, and time. Whole nations live here, dance here, farm here. It's easy to forget that all of it sits atop magma chambers that could, with the right spark, change everything. But for now, the volcanoes slumber. The smoke curls gently. The magma murmurs below. And you, small visitor, are reminded that the Earth is not just alive, it is dramatic. The ground shifts beneath your feet, not in a cinematic, world-ending way, but in that eerie, animal-sensing, something-is-wrong kind of way. You freeze, breath held. A bird lifts off a fence post, a dog barks, and then silence. A second later it hits. The sudden jolt, the sideways sway, the deep guttural groan of the earth moving. You've just walked into an earthquake zone. Unlike the showy fireworks of volcanoes, earthquakes come without much warning. There's no glowing lava, no poetic plume of ash, just a crack, a slip, and an incredible release of stored energy. You're at a fault line, and whether it's famous or forgotten, it's always waiting. You crouch beside a jagged break in the ground, a reminder that Earth is frankly terrible at keeping it together. This is a transform boundary, where tectonic plates grind past each other, locked in a friction-filled game of tectonic chicken. The stress builds and builds, and then, with the gentleness of a thrown piano, it slips. You're standing near the San Andreas Fault, perhaps the most well-known transform boundary in the world. Here, the Pacific Plate and the North American Plate slide past each other horizontally at a rate of about 3.5 centimeters per year. It's like two massive conveyor belts brushing shoulders and occasionally dislocating a city or two. In 1906, San Francisco learned this lesson the hard way. The Great San Francisco earthquake ruptured 477 kilometers of fault line in under a minute, with some areas shifting over 6 meters. Historians still argue whether the subsequent fires did more damage than the quake itself, but either way, the city was reshaped in hours. And here's the strange thing, the fault itself isn't always easy to see. You expect a big canyon or a glowing chasm, but most of the time, it's just a quiet crack running through hills, backyards, or parking lots, until it moves. But not all faults are transform boundaries. You pass over a normal fault, formed when plates pull apart and a chunk of earth slips downward, and then a reverse fault, where plates push together and force the crust upward. Each fault has its own personality, its own stress patterns, its own disasters waiting to happen. A quirky fact: earthquakes don't just happen on Earth. We've recorded moonquakes thanks to the seismometers left behind by Apollo astronauts. They're less violent but still real. The Moon, with no tectonic plates, has quakes caused by gravitational tugs and thermal expansion. Historians still argue whether Mars has true tectonic faults, or if its quakes, Mars quakes, come from cooling and cracking crust. Either way, the solar system likes to shake things up. Back on Earth, you're moving through a quiet fault line now, one that hasn't ruptured in hundreds of years. The grass grows peacefully, houses are built unknowingly above it, and even the animals seem indifferent. But beneath the surface, pressure is building. These locked faults are the scariest kind. They accumulate stress silently for centuries, then release it in seconds. The 2004 Indian Ocean earthquake, for example, ruptured a subduction zone fault that hadn't moved in generations. The result was a magnitude 9.1 to 9.3 quake and a tsunami that travelled across the ocean at jet speed, claiming over 230,000 lives. The Earth, when it shifts like this, doesn't discriminate. It doesn't send invites or RSVP cards. It just moves. And earthquakes don't always strike where you expect. Some of the most dangerous zones aren't at plate boundaries at all. In the central United States, for instance, the New Madrid seismic zone sits smack in the middle of the North American plate. In the early 1800s, it unleashed a series of massive quakes that caused the Mississippi River to flow backward temporarily. Residents were understandably unsettled. Why do quakes happen in these quiet interiors? Historians still debate whether they're reactivations of ancient faults, far-field stresses from plate edges, or something else entirely. But they prove one thing: no part of a tectonic plate is truly stable. It's just a matter of how long it's been pretending. You duck into a small building retrofitted for seismic safety. Steel bracing, flexible foundations, the works. These modern designs try to outsmart the quakes, allowing structures to sway and bend rather than crack and crumble. Japan, Chile, New Zealand. They've all learned from hard-earned experience how to build for a moving Earth. But what about warning systems? Well, we've gotten better. In some countries, early warning networks detect the initial less damaging P waves and send alerts before the more destructive S waves arrive. It's not a lot of time, maybe seconds, sometimes a full minute, but it can be the difference between catching an elevator or getting stuck in one. You press your hand against the ground, it's quiet again now, no tremors, no jolts, just the knowledge that you're sitting on a massive tension wire, stretched across 1 billion tons of rock. Earthquakes may seem sudden, but they're anything but. They are the final exhale of slow, unrelenting stress, and each one draws new fault lines, geological and emotional, into our maps. A few more steps and you're walking over a stretch of land scarred by a recent quake. The earth split open here, fences no longer line up, roads kink like bad origami, but nature's already patching it back together. Grass grows in the cracks, birds return, people rebuild, the planet doesn't pause, neither do we. And that's the paradox of earthquakes. They are terrifying, but also a part of Earth's design. Without them, we wouldn't have mountains, we wouldn't have valleys, we wouldn't have the rich geological chaos that shaped our planet. So the next time the ground trembles, whether you're in Tokyo or Istanbul or somewhere in between, know this: the plates have moved, the Earth has sighed, and everything, for a second, remembered it's alive. You're on the move now, not in a car, not on a train, not even aboard a particularly ambitious glacier. No, this time you're hitching a ride on a tectonic plate itself, specifically the Australian plate, which, believe it or not, is one of the fastest drifting slabs of real estate on Earth. Congratulations. You're coasting through geological history at about 7 centimeters per year. It doesn't sound like much, does it? But think about it this way. That's faster than your toenails grow, faster than the rate your hair creeps down your back in a year. Enough that since you were born, your entire continent may have shifted more than a meter. You, my friend, have been moving your whole life and didn't even notice. Right now, the Australian plate is hurtling northward like a tectonic cruise missile, grinding slowly towards Southeast Asia. It's colliding, converging, and causing all kinds of drama. Indonesia, that's part of the crash zone. New Guinea, right in the way. Eventually, parts of Australia might weld themselves onto Asia entirely, whether the locals like it or not. You glance down at the dry red heart of the outback, and it feels steady, solid. But in truth, the land beneath your feet is on the go, dragged by deep mantle convection and tectonic forces you can't see. The motion is consistent enough, in fact, that it messes with GPS systems. Yep, that's your quirky fact of the night. Australia has had to recalibrate its GPS coordinates because the whole continent has drifted out of alignment. In 2016, officials updated the country's position by 1.8 meters to correct the difference between its actual physical location and what GPS satellites thought it was. Turns out, even satellite-based navigation needs a geologic reality check once in a while. You shift now to the Pacific Ocean, where island chains like Hawaii stretch like beads on a string. These aren't random, they're the breadcrumbs of tectonic drift. Each island in the Hawaiian chain marks a former location of the Pacific Plate as it slid over a stationary hotspot in the mantle. The hotspot stays still, the plate moves, new island forms, repeat. The big island is currently sitting over the hotspot, which is why it's still volcanically active. The older islands, Maui, Oahu, Kauai, are extinct, weathered, and slowly sinking back into the sea. It's geological time-lapse photography, only slower. You glide over Iceland, where the North American and Eurasian plates are pulling apart at about 2.5 centimeters per year. That's right, Iceland is growing, very slowly, but undeniably. This divergence causes regular quakes, fresh lava fields, and occasional panic among local sheep. The Earth is not a static stage, it's a moving platform, and the speed of plate motion varies. Some are snail-like, less than a centimeter per year. Others, like the Nazca Plate, rush towards South America at over 10 centimeters per year, shoving themselves under the continent with enough force to create the towering Andes and the occasional serious earthquake. But speed isn't just about drama, it's also about consequences. Fast-moving plates cause more intense compression at collision zones, which leads to bigger quakes, faster mountain uplift, and more rapid subduction. It's the geological equivalent of braking hard in traffic. Something's going to get crunched. Historians still argue whether the speed of continental drift has changed over Earth's history. Some models suggest the plates were more sluggish in the past due to a hotter mantle. Others argue that supercontinent cycles naturally vary the pace. It's like trying to figure out if the Earth was a morning person 3 billion years ago. Tricky business. And then there's North America, creeping steadily westward thanks to the spreading of the Atlantic Ocean. At about 2.3 centimeters per year, it's not going to win any races, but give it time and it'll get there. In 200 million years or so, you might be able to walk from New York to Tokyo, though the weather might be dramatically different. You land now in California, near the infamous San Andreas Fault. One side of the fault, on the Pacific Plate, is sliding northwest. The other, on the North American Plate, is heading southeast. In a few million years, Los Angeles could be a neighbor of San Francisco. Real estate prices, already horrific, will no doubt remain unchanged. Time for a strange but true detour. There's a theory known as true polar wander, not to be confused with plate tectonics, where the entire solid Earth can reorient itself relative to the planet's spin axis. Basically, the crust and mantle can shift as a whole, like a grape rolling inside a gelatin mold. Historians still debate whether this has happened during Earth's past, and whether it could explain some oddly oriented mountain belts or ancient tropical fossils found in polar rocks. Back to your plate ride. What does it feel like to drift geologically? Well, it feels like nothing. That's the thing. You're always moving, but your brain doesn't register it. It's like being on a massive, ultra-slow escalator that takes 100,000 years to reach the next floor. And yet, over time, it changes everything. Where continents sit affects climate. When South America connected with North America, it blocked off ocean currents and reshaped global temperatures. When India crashed into Asia, it lifted the Himalayas and helped cool the planet. Plate motion controls what land touches what ocean, which controls what winds blow where, which controls which forests grow, which determines what creatures evolve. You are drifting, always have been. So take a moment, feel the earth under you, not just as a place, but as a vehicle. You are not sitting still. Your continent is on a journey, slow, stubborn, and inevitable. You are the cargo of crustal ambition. The sun is high now, and you're somewhere humid. Maybe South America, maybe Africa, hard to say. You're standing in the middle of a grassy plain, the kind that feels untouched, ancient. But buried in the dirt around you are clues that rewrite the map. Bits of bone, imprints of leaves, even the outline of a jaw. Fossils scattered like breadcrumb evidence from a planet that once looked very different. And these fossils, they didn't get the memo about the continents drifting apart. You brush away some loose soil and find a familiar friend, Mesosaurus, a small freshwater reptile with paddle-like limbs. It lived around 280 million years ago, slithering through lakes and rivers like a toothy otter. Its fossilized remains show up in southern Africa and in South America, neatly divided by the vast Atlantic Ocean. Now, unless Mesosaurus was secretly into open ocean swimming marathons and forgot to invent boats, there's only one explanation. Those continents were once joined. This is one of the most compelling lines of evidence for continental drift. Identical fossils, plants, reptiles, even trilobites, found on opposite sides of oceans, and not just similar species, the exact same species, trapped in ancient rock strata now separated by thousands of kilometers of water. A prehistoric game of copy-paste, interrupted by tectonics. You follow a path of fossil clues, and each step feels like a flashback. Glossopteris, a fern-like plant with tongue-shaped leaves, shows up next, fossilized across Antarctica, India, Australia, and South America. That's a big plant to be getting around without frequent flyer miles. But again, not a traveller, just a resident of Gondwana, the southern half of the supercontinent Pangaea, before it fragmented and scattered its fossils like confetti. Historians still argue whether the presence of similar fossils in Antarctica proves it was once warm, or simply connected to warmer continents. Either way, the frozen southern landmass you're standing on, it was once lush with forests and flowing rivers, where dinosaurs might have strolled without parkas. You press your hand to the rock and feel not just heat, not just weight, but memory. This crust has moved. These fossils have shifted, and somewhere beneath your feet is the ancient trail of their drift. Of course, not everyone believed this at first. When Alfred Wegener first proposed the idea of continental drift in 1912, he wasn't met with applause. He was a meteorologist, after all, not a geologist, and he dared to suggest that continents could move. At the time, most scientists believed the continents were fixed, immobile features of the Earth. But Wegener had his evidence: fossil distribution, matching coastlines, glacial striations pointing toward the equator, and strange climatic data from now frozen lands. His favourite trick, cutting out a map of the continents and showing how they could be slid back together, like pieces of an ancient jigsaw puzzle that had been tragically left in a washing machine. And yet, despite all this, Wegener couldn't explain how the continents moved. No motor, no mechanism. That, more than anything, got him laughed off the geological stage. It wasn't until the mid-20th century, with discoveries like seafloor spreading, magnetic striping, and subduction zones, that his theory found its legs. But the fossils, they were always telling the truth. You now walk across the floor of an ancient rift valley. The sediment beneath your feet is packed with prehistoric bones, some mammalian, some not. In places like the East African Rift, You can find early hominid fossils that hint at humanity's own tectonic inheritance. Our ancestors evolved near a dynamic landscape, shaped by shifting plates, volcanic activity, and ever-changing climates. You're not just the result of evolution, you're the result of plate tectonics too. Quirky little fact, there's a type of rock called tillite, formed from ancient glacial debris. It shows up in now tropical regions like India and Brazil. Why? Because when those rocks formed, those continents were near the South Pole. The rocks remember, even if the weather forgot. And it's not just fossils that tie these ancient lands together. You find matching mountain ranges across different continents. The Appalachians in North America align perfectly with mountains in Scotland and Norway. It's as if someone took a massive seamstress's tape and measured the folds of Earth across oceans. Turns out the crust remembers its friends. Historians still argue whether some fossil finds, especially fragmentary or ambiguous ones, are truly evidence of continental unity or just convenient coincidence. But the pattern is too strong, too precise. The same species appearing in matching rock layers across disconnected continents tells a very clear story. Once, we were one. And speaking of matching layers, you stoop to examine a band of red sandstone in the Namib Desert. It looks strikingly like formations found in Brazil. In fact, geologists have long noted rock strata continuity across the Atlantic, right down to the types of sediment, the mineral makeup, and even the tilt of the layers. It's like pages of the same book were ripped apart and stored in different libraries. But the fossils are still the most poetic evidence. Creatures that never knew oceans, some that couldn't even swim, now lie split across continents, their bones acting as stamps of ancient unity. You pick up a trilobite fossil, its tiny segments frozen in stone. These little guys went extinct over 250 million years ago, but their presence on multiple modern continents is another whisper of an Earth once unbroken. What's wild is how many of these fossils were found before plate tectonics was widely accepted. Victorian scientists puzzled over them. They theorized land bridges, like the imaginary Lemuria, a proposed landmass to explain fossil links between India and Madagascar. People invented all kinds of wild theories to explain the data, and all the while, the answer was right beneath their feet. The continents move. You exhale and glance around. The wind rustles tall grass, the sun dips low. Everything seems fixed, still, but you know better. The fossils in the ground tell a story of motion, not just of species and time, but of land itself. And like a detective piecing together a shattered globe, you realize that every matched fossil is a clue to where we once were, and where we might drift next. You're underwater again. No surprise there. After all, the ocean covers over 70% of Earth's surface, and it's where some of the planet's most revealing clues are hidden, layered in darkness. You float gently above the deep blue, but this time, you're not watching for whales or chasing down a lost boot from the Titanic. No, you're here for something stranger. Magnetic stripes laid out across the ocean floor like barcode tattoos. These aren't visible to the eye, but if you could tune into Earth's magnetic memory, you'd see them. Long symmetrical bands of rock with alternating magnetic orientations. And they're not just cool looking, they're proof that Earth records its own history, one field reversal at a time. Let's back up a second. The Earth has a magnetic field created by the movement of molten iron in its outer core. It acts like a planetary shield, protecting us from solar radiation and guiding migrating animals, and of course, your old-school compass needle. But every now and then, something strange happens. The field flips. North becomes south. South becomes north. It's like if your phone screen rotated 180 degrees for no reason and stayed that way for thousands of years. These magnetic reversals are irregular and, frankly, a little rude. They don't follow a pattern and they don't ask permission. Sometimes they happen every few 100,000 years. Sometimes millions pass between flips. Historians still argue whether these reversals are triggered by instabilities in the core's convection or external planetary forces, or whether the field just has a dramatic streak. But here's the part that matters to you right now. When lava cools, especially at mid-ocean ridges, the minerals inside it lock into place with whatever magnetic orientation the Earth's field had at that moment. It's like hitting save on the magnetic setting of the planet. And since seafloor spreading creates new crust symmetrically on both sides of a ridge, these magnetic signatures appear in matching patterns, one on the left, one on the right. You float over the mid-Atlantic ridge and imagine a giant magnetic tape recorder beneath you. As new crust forms and spreads, it captures the latest track. North is this way, south is that way. Then, when the field reverses, the next batch of lava records a different track. Over time, you get a striped ocean floor, encoding a timeline of Earth's magnetic drama. In the 1960s, this discovery was the mic drop moment for plate tectonics. Scientists had already suspected that the continents moved and that seafloor spreading existed, but these symmetrical magnetic bands were hard, unambiguous evidence. You couldn't fake that kind of pattern. It was the geological equivalent of finding matching fingerprints on both sides of a crime scene. You drift deeper now, into the abyssal plains, far from any sunlight. The ocean floor stretches for miles in every direction, quiet, cold, and consistent. And still, beneath the sediment, the magnetic memory persists. Instruments towed behind ships or embedded in seafloor observatories quietly read these patterns, building a magnetic history of the planet layer by layer. A quirky detail for your inner trivia collector. Earth's last full magnetic reversal, the Brunnes-Matuyama reversal, happened about 780,000 years ago. That's a blink in geologic time. Some scientists believe we're overdue for another one. In fact, the South Atlantic anomaly, a weakening area of Earth's magnetic field, has made a few eyebrows raise. Could it be the start of a reversal? Maybe, maybe not. As always, Earth doesn't RSVP, but let's say the field did flip tomorrow. What would happen? Well, your compass would lie to you. Birds might fly in confused circles for a while. Satellites and electronics could take a hit due to reduced shielding from solar radiation. But life would likely go on. Reversals have happened dozens, possibly hundreds of times in Earth's history, and the fossil record doesn't show any mass extinctions linked to them. So, probably not the apocalypse. Just another example of Earth being casually chaotic. You ascend slightly now, hovering over the East Pacific Rise, another major spreading centre. It's much faster than the mid-Atlantic ridge. Crust forms here at about 15 centimetres per year, compared to 2 to 5 centimetres in the Atlantic. As a result, the magnetic stripes are more spread out. The record plays at different speeds in different places. Here too you find the matching magnetic bands, striped patterns that echo through the crust. Each one a chapter in the Earth's autobiography, each one laid down in fire, frozen in stone, and translated by scientists with magnetometers and far too much coffee. Historians still argue about the exact timing of some older reversals. Radiometric dating gets you close, but oceanic crust eventually gets recycled in subduction zones, so older records are lost. The oldest intact ocean floor we have is about 200 million years old, younger than the earliest dinosaurs. Everything before that, gone, eaten, recycled. That's one of the strange things about Earth. Its surface is constantly rewriting itself. Unlike the Moon or Mars with ancient unchanging crust, Earth's face is a rough draft that keeps editing itself. The continents get shuffled, the oceans open and close, and through it all the magnetic stripes endure until the crust itself is destroyed. You pause over a fracture zone, one of those long offset cracks that interrupt the continuity of the ocean floor. These are reminders that even the spreading process isn't neat. The crust doesn't glide apart in elegant curves, it fractures, it hesitates, it throws in a few transform faults for good measure, and still, the magnetism records it all. As you rise once more toward the surface, a thought sticks with you. The ocean floor doesn't just support the sea, it's a time capsule, a memory palace built from iron and lava. And it has a story to tell, one reversal, one stripe, 1 centimetre at a time. So next time you're at the beach, toes in the surf, remember that somewhere out there beneath the waves is a lava-made library, quietly holding the secrets of a planet that can't stop flipping the script. Now you're floating over a string of tropical islands that seem plucked from a postcard, lush, volcanic, and impossibly remote. The waves glitter below, palm trees sway in the breeze, and the ground beneath your feet is actually a mountain, just one whose summit pokes above the ocean's surface. You're in Hawaii, and while the ukuleles and shave ice are nice, you're here for what lies far deeper. Because this place isn't just paradise, it's one of Earth's weirdest geological quirks, a hotspot. Unlike most volcanic activity, which happens at plate boundaries, hotspots are intraplate features, meaning they exist smack in the middle of tectonic plates, far from any boundary drama. They are, in a word, rebels, quietly doing their thing, building islands, and not caring whether they fit in. A hotspot is a plume of superheated mantle material that rises from deep within the Earth, possibly as far down as the core mantle boundary, over 2,800 kilometers below your sandals. It pierces the lithosphere like a blowtorch through a cracker, melting rock and forming volcanoes above. And here's the key. While the plume stays more or less stationary, the plate above it keeps moving. That's why Hawaii isn't one giant island. It's a chain, a geological breadcrumb trail showing exactly where the Pacific plate has drifted over time. You hover over the big island of Hawaii, which is still very much alive, volcanically speaking. Its two main volcanoes, Mauna Loa and Kilauea, are among the most active on the planet. You might even catch a glimpse of lava flowing gently, well, let's hope it's gentle, into the sea, sending up plumes of steam that look oddly like the Earth exhaling. Just northwest lies Maui, older and quieter. Then Oahu with its dormant peaks. Keep drifting along the chain and you'll eventually reach Kauai, worn and weathered, its once mighty volcanoes now little more than green-cloaked hills, and beyond that, just seamounts, underwater mountains like Loihi, the next volcano in waiting currently building itself up beneath the ocean. All of these were born from the same hotspot. It's the perfect natural conveyor belt. New islands form over the hotspot, then drift northwest with the Pacific plate. As they move away from the plume, their volcanic activity slows, then stops. The island begins to erode, sink, and eventually vanish beneath the waves. The hotspot, meanwhile, continues punching upward, starting the cycle all over again. A quirky side note for your mental travelogue. Mauna Kea, one of the Big Island's extinct volcanoes, is technically the tallest mountain on Earth, from base to summit. Its base sits far beneath the ocean, so while Everest wins above sea level, Mauna Kea beats it in total height, which means you're basically in the Himalayas of the sea. Bring a jacket. Scientists have identified other hotspots around the world too. Yellowstone, for example, is believed to sit atop a different mantle plume. But unlike Hawaii, Yellowstone's hotspot is under continental crust, thicker and less easygoing, which means it produces super eruptions instead of graceful island arcs. Drama queens, really. There's also Iceland, where a hotspot happens to align with a mid-ocean ridge. The result? One of the few places on Earth where you can watch new crust form on land, over a volcanic plume, and still make it back to your hotel in time for dinner. But let's get back to Hawaii, where everything you see is the direct result of a stationary source of heat meeting a moving plate, and it's still happening. You kneel and touch a cooled lava rock just weeks or months old. It's warm from the sun, not the eruption, but it hums with recent memory. Beneath you, the Pacific plate is still inching northwest, pulling the big island away from the hotspot even now, and below that, the plume continues to rise, slow and relentless, like a planetary fountain that never runs dry. Historians still argue whether hotspots are caused by deep mantle plumes rising from the core mantle boundary or from shallower convective upwellings. The evidence is tricky. We can't exactly look down there, only infer things through seismic imaging and indirect data. But whether the plumes are deep-rooted or just upper mantle mischief, they exist, and they don't move. That's the kicker. It's like having a blowtorch aimed at a slowly moving treadmill. The surface scorches in a line, each burn mark recording where it once stood. This entire system, hotspot and plate, gives us not just islands but timelines. By dating the volcanic rocks along the Hawaiian chain, scientists can calculate the speed and direction of the Pacific plate over millions of years. It's one of the best natural clocks we have for tracking plate motion. And as you float farther out, you begin to notice something odd. The island chain bends. Around the Emperor Seamounts, the line shifts direction, like someone tugged the ribbon and gave it a kink. This bend happened about 47 million years ago, and it tells us something major changed. Probably the direction of plate motion. It's subtle, but incredibly informative. The rocks remember. The ocean floor doesn't forget. You drift now over Midway Atoll, a quiet place with more birds than people. It's near the older end of the Hawaiian Emperor chain, once a volcanic island itself, now mostly reef. One day, the big island will look like this. Then eventually it'll sink beneath the waves, because nothing on a hotspot lasts forever. You look back toward the southeast, toward the glowing horizon where Loihi is still forming. In 10,000 or 100,000 years, it may rise above the sea and take its place in the island chain, A new island, a new chapter. That's the magic of hotspots. They're subtle, steady, and long-lived. They defy the usual tectonic rules, and yet they're essential to understanding Earth's deeper patterns, like a hidden track on an album you thought you knew by heart. So the next time someone points to Hawaii on a map and sighs about island life, you'll smile just a little and think, yes, paradise, but also proof. A perfect geological diary entry left behind by a plate that never stops drifting over a planet that never stops writing. You're hovering now just above the Earth's crust, not way out in space, not deep down in the mantle's glowing taffy, but right there at the meeting point. The lines, the cracks, the seams. You've followed the drifting plates, the crashing mountains, the underwater rifts and searing volcanoes, but now it's time to really look at what we call plate boundaries, and realise that calling them lines is kind of like calling a wildfire a campfire. That they're not tidy, they're not just cracks on a map. They're entire regions, zones of bending, breaking, melting, trembling, and despite how we draw them in geology textbooks, they're not always so simple. Let's start with the textbook types. You've met them before, but now we'll get a little closer. First up, divergent boundaries. These are where plates pull apart, usually under oceans but sometimes on land. Mid-ocean ridges like the Mid-Atlantic Ridge are classic examples, where magma rises, solidifies and creates new ocean floor like a giant lava zipper. But sometimes this pulling apart happens on continents too. You're now standing in East Africa, gazing across the vast East African rift system. It's a crack that runs for thousands of kilometers, stretching from Ethiopia to Mozambique. The continent here is literally tearing itself in half, slowly birthing a new ocean between future Africa West and future Africa East. The ground is fractured, lakes fill in the gaps, volcanoes rise where the crust is thinning. And no, this isn't theoretical. In parts of Ethiopia, you can walk along a crack in the earth that opened overnight. Not centimeters, meters, and it's still growing. Historians still argue whether East Africa's rift will fully evolve into a new ocean basin, or if it might stall, like failed rifts from Earth's past. But the process is underway, and it's as real as the steam rising from nearby hot springs. Next, you're off to a convergent boundary, where plates collide. You've already stood in the Himalayas, where continent meets continent and nobody yields. But just south of there, in places like Sumatra, it's oceanic crust diving beneath a continent again. That's a subduction zone, and it creates megathrust faults, volcanic arcs, and tsunamis when it gets feisty. And here's where things start getting messy. You see, boundaries aren't always clearly one type. Some are composite zones, places where plates both slide and crash, both pull and grind. For example, the area around New Zealand is a tectonic spaghetti bowl. The Pacific plate dives under the Australian plate in the north, but to the south, the plates slide past each other more like a transform boundary. In between, a whole buffet of faulting styles. Then you have transform boundaries, the side shufflers. These are the cracks where plates move laterally, like roommates passing each other in a hallway, trying not to touch. The San Andreas Fault is the classic example, but it's not a single line. It's a zone, with multiple fault strands, splays and offshoots. Some are active, others are silent, for now. You drift down now into California, and if you zoom in, you'll see how messy this gets. The San Andreas Fault isn't a perfect smooth feature. It bends, it splits, it jumps from one rock type to another, and around each bend, stress builds differently. One spot might slip quietly, another might be waiting for the big one. Quirky side fact, some parts of transformed faults creep. That's right. Instead of storing up stress for a big earthquake, they move quietly and constantly, like tectonic stress doing yoga. The town of Parkfield, California, even markets itself as the earthquake capital of the world, because it sits on one of these creeping zones, with regular, modest tremors that help scientists monitor tectonic movement in real time. You're floating over boundary types now like a geologist on an espresso binge. But wait, it gets even weirder. Some plate boundaries are so diffuse, so spread out, that it's hard to say exactly where one plate ends and another begins. The Himalayan collision? Sure, the plates meet. But the zone of deformation stretches over hundreds of kilometers. Faults lace through the landscape like cracked porcelain, and the collision has warped the entire Tibetan plateau. Even intraplate areas, supposedly stable interiors of plates, can behave like boundary zones. Take the New Madrid seismic zone in the central US. It's a leftover wound from a failed rift system, called an orlicogen, if you want to sound fancy at dinner parties. It's not on a current plate boundary, but it still experiences earthquakes because the old scar tissue still responds to far-field tectonic stresses. In other words, the plate boundary might be long gone, but the damage lingers. Historians still argue over what to call these weird edge cases: microplates, sliver plates, diffuse margins. Some plates are entire oceans, others are smaller than Texas, like the Juan de Fuca plate, trying very hard to subduct itself beneath North America while nobody pays much attention. And sometimes plates don't even behave like plates. Some regions behave more like deforming blobs than rigid slabs. Scientists call this distributed deformation, and it challenges the neat idea of tectonic plates moving as unbending chunks. You walk now along the Caribbean plate, a strange in-betweener that's being squeezed, scraped and rotated by the surrounding giants: North America, South America, and the Atlantic Ocean floor. The result? Complex fault zones, volcanic islands, and frequent earthquakes from multiple directions. It's a good reminder that our tidy tectonic map, the kind you see in textbooks with red arrows and neat boundaries, is a simplification. A helpful one, yes, but real Earth is fuzzier, messier, alive, and sometimes the boundary isn't where we think it is. Some researchers now believe that the Antarctic plate might be more active than once thought, hiding tiny microplates under the ice. Others argue about the Somali plate, which may be splitting off from Africa, forming its own drifting landmass. The more we study, the more it seems that Earth's crust is not just broken into a few big slabs, but dozens of shifting, evolving pieces. You stand now at a triple junction where three plates meet. The boundaries overlap, zigzag, and tangle beneath your feet. It's not just a point, it's a conversation, and the Earth, as always, is still figuring out what it wants to do. So next time you see a map with thick black lines labelled plate boundary, remember, the Earth doesn't do clean lines. It does zones, it does gradients, it does chaotic beauty. Plate boundaries aren't just where continents meet, they're where the planet negotiates with itself. You're standing still now, completely still, or at least you try to be. The landscape around you is frozen in time, no earthquakes, no eruptions, no drifting mountains. The air is still, the seas are calm, and the planet dead quiet. Because in this thought experiment, plate tectonics has stopped. No more drifting continents, no subduction, no seafloor spreading, no volcanic arcs. The conveyor belt is off, the inner engine is stalled, Earth's restless crust has finally tapped out. You step across a cracked plain that hasn't moved in millennia. Fault lines, dormant, mountain ranges, crumbling. Without tectonic movement, there are no fresh uplift zones, so erosion is slowly sanding everything down. The Himalayas, once towering, are being chewed into hills, the Alps worn to nubs, the Rockies just bumps in the background. Without plate motion, the Earth becomes quieter, but also more vulnerable. Let's start with the obvious. No more new crust. Mid-ocean ridges, once vibrant with rising magma, are now just cold scars across the seafloor. That steady production line of oceanic crust, gone. Which means, over time, Earth's surface starts to look old, stale, eroded, and then there's volcanism. With no subduction, no rifting, and no crustal compression, most of Earth's volcanoes go extinct. Not all. Hotspots like Hawaii might keep puffing along for a while, since they're driven by deep mantle plumes. But even they would struggle eventually. The surface crust without motion becomes thick, cold, and stable, hard for plumes to punch through. So yes, the planet gets quieter, less dramatic, but also less habitable. You see, tectonics isn't just about shaping land, it's Earth's way of regulating its climate, refreshing its surface, and cycling essential elements. Shut it down, and the side effects start piling up. Let's talk carbon. Right now, Earth balances carbon dioxide between the atmosphere, the oceans, and the crust. Subduction zones drag carbon-rich sediments deep into the mantle, while volcanoes release it back into the air. It's a carbon thermostat keeping Earth from freezing over or boiling away. But if tectonics stops, that loop breaks. No more subduction means no more carbon burial. No more volcanoes means no more carbon release. Over time, Earth's atmosphere could become carbon-starved, temperatures could drop, and global climate could plunge into deep freeze. Or, if carbon stays locked in the atmosphere with nowhere to go, it could have the opposite effect, a runaway greenhouse. Historians still argue which way it would tip. Either way, it's bad news for summer vacation plans. You walk across a vast flat seafloor. No more new oceanic crust has formed in tens of millions of years. The existing crust, once born hot and buoyant, has cooled and sunk. With no recycling, the ocean basins deepen, sea levels drop, coastlines retreat, continents swell as erosion dumps massive loads of sediment into the basins. Over time, the whole system becomes sluggish, top-heavy and unbalanced. A quirky side effect? Earthquakes disappear. Well, almost. With no plate movement, there's no stress build-up along faults. Cities once devastated by tremors now sit in eerie stillness. Insurance companies breathe a sigh of relief. Seismologists get bored. You walk through Los Angeles and the San Andreas fault lies still, like an unplugged wire. Nothing has shifted in ages, but don't get too comfortable. Stillness, on geological timescales, isn't stability. With no tectonic motion to vent heat, Earth's internal energy has nowhere to go. Slowly, the mantle heats up, pressure builds, and the lithosphere becomes a brittle lid. It's a bit like putting a pressure cooker on the stove and losing the release valve. Eventually something has to give. Some geologists theorize that if plate tectonics were ever to completely stop, Earth might build up so much internal pressure that it would undergo a catastrophic resurfacing event. A planet-wide outburst of heat and magma resetting the crust entirely. Venus might have done something similar. It's covered in basalt plains that suggest its entire surface was recycled in one massive event, possibly due to the absence of active plate tectonics. You look up now, the sky's familiar but the atmosphere feels thin. Without tectonics, nutrient cycling slows, mountain ranges stop rising, and with them, the input of fresh rock for chemical weathering, a key process that draws CO2 out of the air. Plant life thins. Ocean life suffers from lack of phosphorus and other essential elements, once carried by rivers from rising highlands. The biosphere begins to suffocate slowly, not from catastrophe, but from geological boredom. And without tectonics, biodiversity suffers. No more isolated island arcs, no more land bridges forming and vanishing, no rift valleys to divide populations and force new adaptations. Evolution, which thrives on disruption, gets sleepy. You kneel beside an old rounded mountain. There are no earthquakes here, no volcanoes, no continent colliding just out of view, only the wind wearing it down grain by grain. You can almost hear Earth sigh. Historians still debate whether plate tectonics is a permanent feature of Earth or just a temporary phase. Some think it began around 3 billion years ago, when the planet finally cooled enough for solid plates to form. Others suggest it started much later, and some propose that it could one day stop for real, when the mantle cools too much to drive convection, or when water, which lubricates subduction zones, becomes too scarce. But for now, it hasn't. For now, Earth still breathes, shifts, remakes itself, and thank goodness. Because without tectonics, Earth becomes something else. Not dead exactly, but static. A planet on pause. You rise again and imagine it. A world with no earthquakes, no volcanoes, no new mountains. A smooth-skinned Earth, peaceful, predictable, and eventually, silent. The wind picks up now, not with urgency, but with that deep, slow rhythm of time passing. It brushes past your face like an old story being told again. You look down, and beneath you lies a massive, shifting mosaic of land masses, continents on the move, oceans stretching and folding, and right at the heart of it all is a rhythm so old, so slow, and so persistent that it shapes the entire planet without ever needing to rush. This is the story of supercontinents, and how they keep coming back. Right now, we live in a world of scattered continents, North and South America to the west, Africa and Eurasia to the east, Australia wandering upward like a curious turtle. But zoom out, stretch your mind across deep time, and you'll see it. Earth has a cycle. Over and over, the continents come together, form a single supercontinent, break apart, and drift again. It's called the supercontinent cycle, and it plays out on a timescale of roughly 300 to 500 million years. It's not perfectly regular, like a ticking clock, but the pattern is there. Slow pulses of assembly and breakup that drive everything from mountain formation to ocean chemistry. The most recent supercontinent you probably know, Pangaea. Formed around 335 million years ago, it stitched together nearly every landmass into one sprawling, mostly southern hemisphere lump. A few hundred million years later it shattered, and the pieces began the long drift toward where they are today. But Pangaea wasn't the first. Far from it. Before Pangaea, there was Rodinia, formed about 1.1 billion years ago. It included most of Earth's continents too, but in a very different arrangement. Think of it as the awkward older sibling of Pangaea with different tectonic taste. Rodinia eventually broke up, giving way to new ocean basins and strange microbial ecosystems. Go back further still, and you get Columbia, also called Nuna, at around 1.82 billion years ago, and maybe Kenorland even earlier. The exact number of supercontinents is still debated. Historians still argue whether these early clusters were true supercontinents or just tightly knit continent cliques. But one thing's clear, Earth has done this dance before, many times. You float now above a hypothetical model of what the Earth might look like in 250 million years. Scientists have a name for this future supercontinent, Pangaea Proxima, or sometimes Next Pangaea, or even Amasia, if the northern continents do most of the uniting. The exact future shape depends on which model wins the argument, but the possibilities are incredible. In one version, the Atlantic Ocean closes and the Americas crash back into Europe and Africa, reuniting the family more or less. In another model, the Pacific closes instead, and Asia slams into the Americas from the west. Either way, the continents don't just wander, they're heading toward another massive group hug. Just a very slow one. And it's not just about the land. When supercontinents form, they trigger massive changes in the planet's systems. First, there's the climate. Supercontinents often come with extreme weather patterns. With so much landmass clumped together, moisture has a hard time getting into the interior. That means massive deserts, huge seasonal temperature swings, and possibly even global cooling, since weathering on newly formed mountain belts can draw down atmospheric CO2. Then there's the life. When continents join, species from separate ecosystems suddenly mix, often leading to bursts of evolution or mass extinction events if the environmental changes are too rapid. When they break apart, isolated populations go their separate ways, evolving along different paths. Tectonics, quite literally, drives evolution. A quirky historical note. The Cambrian explosion, that famous bloom of complex life around 540 million years ago, happened shortly after the breakup of Rodinia. Some researchers believe the breakup may have increased nutrient flow into the oceans and shaken up ecological niches, setting the stage for life to explode in complexity. Geology. It's not just rocks, it's a life accelerator. You look back now at a time-lapse of Earth's crust. Continents collide, mountains rise, oceans squeeze shut and open elsewhere. The surface of the planet breathes in slow tectonic patterns. It's not just the continents that move, the oceans move with them, born and buried by the cycle. These long-lost oceans have names, by the way. Ever heard of Iapetus? Not the Moon, the ocean that once lay between the ancient continents of Laurentia and Gondwana, long before the Atlantic existed. Or Tethys, which separated Africa and Eurasia before it closed to form the Mediterranean. Each one had its time. Each one vanished under the plates it once parted. Historians still argue what exactly drives the supercontinent cycle. Is it the cooling of Earth's mantle, the balance between ridge push and slab pull, or just an inevitable pattern based on the physics of crustal plates floating on a round planet? The answer is likely a bit of all of it. One thing's for sure, plate tectonics doesn't just drift continents around, it orchestrates them, brings them together for the big shows, then scatters them again for solo acts. You pause now on the ancient shield of Canada, part of one of Earth's oldest cratons, stable pieces of continental crust that have survived multiple supercontinent cycles. This rock beneath your feet is over 3 billion years old. It has seen it all, been part of different supercontinents, broken off, rejoined. It's like geological royalty, scarred, weathered, and unshakably still. And so you realize, the continents aren't drifting randomly. They are part of a deep, slow rhythm that plays out over eons, a tectonic waltz that never truly ends. The next supercontinent? It's already starting, very, very quietly. You can't hear it, but you're standing on it. You step carefully now, as if walking across something fragile, though of course, what you're walking on hasn't existed for millions of years. The waves lap at invisible shores, the wind drifts across landscapes that only live in memory. Because here, beneath your feet and behind your gaze, are lost oceans and ancient highways. vast corridors that once connected lands and lives now separated by entire hemispheres. The map you know is temporary, always has been. You're walking across Tethys, a long-vanished ocean that once stretched between the ancient supercontinents of Gondwana in the south and Laurasia in the north. Long before the Mediterranean was a gleam in Earth's eye, Tethys shimmered with warm shallows, coral reefs, ammonites, and the slow drift of plates on a silent current. Today, that ocean is mostly gone, closed and buried by the collision of Africa, India, and Europe. But its ghosts remain. The Alps, the Himalayas, the Zagros Mountains, they're all monuments to Tethys's destruction. Every fold in those mountains is a ripple left behind by a shrinking sea. You dig into soft limestone and find a fossilized sea creature, nummulites, disc-shaped protozoans that once drifted through the waters of Tethys. They're found high up in mountain ranges now, sometimes at elevations of 3,000 meters, because in plate tectonics, what once was ocean floor can now be mountaintop. Gravity, it turns out, is negotiable when you're drifting on a plate. But not all the lost landscapes were oceans. Some were bridges. Welcome to Pangaea, an ancient land bridge that once connected Asia and North America during the Ice Ages. Right now, you'd be standing underwater in the middle of the Bering Strait, but rewind just 20,000 years and this spot was tundra. Mammoths roamed, humans crossed. It was a biological highway between worlds, open thanks to low sea levels caused by glaciers locking up water. As ice advanced and retreated, so too did coastlines. Plate tectonics controls the shape of continents, but climate controls where land ends. Pangaea is just one of many such ephemeral bridges. There was Doggerland, once linking Britain to mainland Europe, and the Sunda Shelf, which connected much of Southeast Asia. These were not just thoroughfares, they were habitats, whole ecosystems erased when the seas returned. You drift now across the vanished ocean of Iapetus, predecessor to the Atlantic. When the continents collided to form Pangaea, the Iapetus Ocean was swallowed by subduction, leaving behind folded rocks and matching geological scars on either side of today's Atlantic. You can see its ghost in the rocks of Newfoundland and the Scottish Highlands, like a continental breakup letter written in granite. Historians still argue whether Panthalassa, the vast superocean that once surrounded Pangaea, was truly uniform or dotted with ancient island chains and microcontinents we've yet to fully discover. Most of its crust has long since been subducted, leaving behind a mystery more than a map. What we know of it comes from ophiolites, chunks of ancient seafloor thrust up onto continents during collisions, tiny souvenirs from an ocean lost forever. Now imagine Earth not as a set of continents, but as a system of connected corridors, oceans opening and closing, land bridges emerging and sinking, tectonic plates guiding migrations not just of rock but of life. Evolution doesn't happen in isolation, it happens on a shifting stage, and the tectonic scripts change constantly. You sit on a boulder that was once part of the Tethys seabed, now perched in a vineyard in Italy. Grapes grow where coral once thrived. Sea life is now stone. And beneath the soil, the bones of ancient creatures lie side by side with the quiet hum of Earth's oldest rhythms. Now let's take a quirky detour. Gondwanatheria, a group of extinct mammals that once roamed the southern continents. Their fossilized teeth have been found in places as far apart as Madagascar, India, and South America. For years, scientists debated how they got so far apart, until plate tectonics cleared things up. When Gondwana was whole, these creatures didn't need to travel oceans, they simply walked. Which brings us to another ancient highway, the Isthmus of Panama. You might think of it as just a thin strip of land connecting North and South America, but its formation about 3 million years ago was a game changer. It closed the Central American Seaway, redirecting ocean currents, intensifying the Gulf Stream, and quite possibly triggering the Ice Ages. Oh, and it also allowed the Great American Biotic Interchange, where armadillos, ground sloths, and porcupines wandered north, while bears, cats, and elephants headed south. You lean down and trace your fingers through the rust-red soil of Africa's rift valleys. Once, rivers flowed toward the vanished Tethys, now long gone. The shape of watersheds, the course of rivers, the position of deltas, all are dictated by ancient tectonic tilts. Even the Amazon once flowed westward, toward the Pacific, until the rise of the Andes flipped the drainage like a continental U-turn. Historians still debate how many of these past connections have yet to be discovered. As plate tectonics lifts and folds and erases, it also hides its work. Lost continents like Zealandia, now mostly submerged beneath the Pacific, remind us that even today, we're only seeing part of the puzzle. It's like trying to read a book where half the pages have been torn out and used as coasters. But the signatures remain. You walk through a field in Australia and find ancient glacial striations, scratches carved into bedrock by long-gone ice sheets. These same patterns show up in southern Africa and South America, proof that these lands were once joined near the South Pole. Fossils match, rocks match, climates match, only the names have changed. So what happened to these ancient oceans and bridges? In a word, subduction. Oceans are born at spreading centres and die at trenches. Land bridges rise with falling seas and vanish when water returns. Nothing on Earth's surface is permanent, and that's the point. The Earth is a machine of disappearance and revelation. And as you sit now on a rocky outcrop, once a coral reef, then a mountain, now just a viewpoint, you start to understand. The continents have not only moved, they've changed connections, over and over again. The Earth has built and erased highways of stone, sea and soil for billions of years, and you, tiny traveller, are walking their shadows. Now let's lift off. Not metaphorically, you actually float higher, leaving behind Earth's rustling forests and tectonic shuffles. The blue fades into black. Atmosphere thins. You pass satellites spinning silently, a few blinking like sleepy drones, and soon Earth is below you in full. The plates still drift. The volcanoes still smoulder. But here, from orbit, something else becomes clear. Earth is weird. Because while we talk about plate tectonics like it's inevitable, just part of being a rocky planet, it's not. And as you gaze out toward the rest of the solar system, you start to see the truth. Earth might be the only one doing this dance. Let's start with Mars. From this distance, the red planet is dusty, bruised, and surprisingly calm. No oceans, no clouds. But it wasn't always like this. If you zoom in on Valles Marineris, a massive scar running along the Martian equator, you might think it's a tectonic rift. Like a Martian East African rift. And it is. Sort of. Valles Marineris is over 4,000 kilometers long, and likely formed due to crustal stretching. But despite that, Mars doesn't have plate tectonics. No subduction zones. No drifting continents. Just a thick single-lid crust that's fractured here and there, but essentially static. Why? Well, Mars is smaller than Earth. It cooled faster. Its mantle is less active. Its lithosphere got thick early on and stayed that way. Without the heat and pressure to drive constant convection, the crust never broke into mobile plates. Instead, Martian geology mostly froze in place. Just some volcanic features here, a few rift zones there, and the occasional landslide. Historians still argue whether Mars ever had plate-like behaviour, perhaps in its early years, but today, it's more of a retired planet, still interesting, just not tectonically lively. Now drift toward Venus, Earth's twin in size and mass, but not in behaviour. From above, Venus glows softly in reflected sunlight, but behind that cloud cover, she's a furnace. Surface temperatures of over 460 degrees Celsius, pressure high enough to crush a submarine, and a surface built mostly of lava plains. But here's the kicker. No plate tectonics. Venus's crust seems to be a single lid too, like Mars, and yet Venus has thousands of volcanoes, more than any other planet. They're not from subduction or mid-ocean ridges. They're from internal pressure, pushing upward wherever it can. Imagine a planet without tectonic release valves, letting pressure build up until, boom, it erupts catastrophically. In fact, there's a theory that Venus may periodically resurface itself entirely, in massive, planet-wide volcanic episodes that melt huge portions of its crust. No slow-moving plates, just a reset. Some scientists think the last of these might have happened 500 million years ago. Historians still debate whether this is ongoing or a one-time meltdown, but either way, Venus isn't drifting continents around. Why not? Possibly because Venus has no water. Earth's tectonic system is lubricated by water. Subduction zones rely on water to lower the melting point of rocks, aiding in plate motion. Without it, the crust might stay locked. Water is also crucial in the creation of continental crust. Without water, Venus may have never developed the right kind of crustal recycling to start plate tectonics in the first place. Quirky fact time, despite its terrifying atmosphere, Venus rotates backwards. Slowly. One Venus day is longer than its year, so even time is broken there. Just saying. Back to Earth now, briefly before we swing further out. Our plate tectonic system is unique in the solar system, not just because we have it, but because it works so well. Our planet is the right size, with just enough internal heat, just enough water, and just the right crustal composition to support a mobile lithosphere. And it matters. Tectonics regulate climate, chemical cycles, and possibly even help maintain habitability. Without them, Earth might have ended up like Venus, hot, dry and tectonically dead, or like Mars, cold, brittle, and still. The fact that Earth has remained tectonically active for over 3 billion years may be the single biggest reason life was able to emerge and stick around. Now aim your gaze toward the moons. Take Io, one of Jupiter's brightest children. Io is technically the most volcanically active body in the solar system, but not because of plate tectonics. Its internal heat comes from tidal friction. The immense gravitational pull of Jupiter literally squishes and stretches it like silly putty. This heats up its interior, producing explosive sulfur volcanoes and lava lakes, but no plates, no crustal drift, just chaos. Then there's Europa, another moon of Jupiter, and Enceladus, orbiting Saturn. These are icy bodies, with surfaces of frozen water and possibly oceans beneath. Some researchers have noted that Europa's icy surface seems to behave in a tectonic-like way, plates of ice breaking, spreading and shifting. Could that count as plate tectonics? Historians still argue about that. It's ice, not rock. But the principles may be similar. If tectonics can happen in ice, then maybe Earth isn't quite so special after all. Maybe other worlds are testing out the blueprint, in different materials, different scales, different lifespans, but none so far seem to be Earth-level tectonic planets, with subduction, spreading ridges, transformed faults, mountain chains and magnetic stripes and hotspots punching through like clockwork. You float now in the quiet space between planets. Earth spins below you, blue, cloud-wrapped, clearly alive. It's the only planet we know where the crust moves, where the continents drift, and where the surface is never the same twice. Historians still argue whether plate tectonics is necessary for life, or merely helpful. Some think it's essential, recycling nutrients, keeping the climate stable, promoting complexity. Others think life could survive on a stagnant lid planet as long as there's energy. But either way, on Earth the two evolved together. Life and drift. Organisms and oceans pulled into place by moving crust, heated from below, remixed over eons. As you drop back toward the surface, through clouds, past mountaintops, down into the tectonic hum of the crust, you realize, we don't just live on Earth, we live on a planet that reshapes itself. One of one, so far. You've touched tectonic plates from the inside out, floated above them, sunk below them, watched them build mountains and erase oceans. But now you find yourself back on more familiar ground. There's a city skyline ahead, roads, bridges, sidewalks, a person jogging, a kid eating a very sticky ice cream cone. It all seems so stable, but it's not. None of it is. Because everything humans have ever built, villages, empires, monuments, streetlights, is standing on shifting plates. And whether we notice or not, our lives are tangled up in this slow-motion chaos. Welcome to the complicated relationship between humans and the plates beneath them. You start walking through a city, let's say Istanbul, or maybe Tokyo, or San Francisco. It doesn't really matter. They all sit near active plate boundaries, and in each one, buildings hug faults, railways cross subduction zones, and entire neighbourhoods are built on soft soils that tremble when the Earth so much as hiccups. Humans, for all our cleverness, have a long history of building where we shouldn't. Why? Because tectonically active regions are also incredibly appealing. Volcanic soils are fertile, rift valleys are flat and farmable, subduction zones are near coastlines, great for ports, trade, fishing. So we settle, we grow, we pave over fault lines and assume they'll behave. Sometimes they do, sometimes they don't. Take Naples, for example. Beautiful city, rich history, bustling life, and sitting in the shadow of Mount Vesuvius, one of the most dangerous volcanoes on Earth. Or consider Mexico City, built on a former lake bed in a seismic zone, where soft sediments amplify every shake from distant quakes. Even Los Angeles rests on a complex web of active faults, and not just the San Andreas. Quirky fact, there are over 150 active faults in the Los Angeles basin alone. The Earth here is like a cracked phone screen that someone keeps pretending still works fine. Yet we stay, because tectonics also gives geothermal energy, pulled from volcanic regions, mineral deposits, concentrated by hydrothermal processes along plate boundaries, even mountains, which give us rivers, snowpack, recreation, and water sources, the Andes, the Rockies, the Alps, all born from tectonic compression, all supporting millions of lives. But when tectonics takes, it takes big. You float back in time to Lisbon, 1755, a peaceful November morning, then suddenly a magnitude 8.5 to 9.0 quake strikes off the coast. Buildings collapse, fires spread, and within minutes a tsunami crashes into the harbour, wiping away what the quake didn't. Tens of thousands dead. The Enlightenment shaken, not just geologically but philosophically. Voltaire wrote poetry about it. Immanuel Kant tried to explain it. Historians still argue whether this disaster was the beginning of modern seismology, or just the moment Europe realised how vulnerable it really was. You flip forward to Japan, 2011, a magnitude 9.0 megathrust quake off the Tohoku coast, a tsunami 40 metres high in places, entire towns erased, a nuclear meltdown, and all from a boundary that had been quiet for centuries. That's the thing, these zones store energy for a long time, and when they release it, humans rarely have time to respond. Our buildings aren't always ready, our evacuation plans are optimistic, and our memories? Short. But we're learning. In places like Chile, New Zealand, and Taiwan, building codes are strict. Structures are designed to flex, not fall. Seismic early warning systems buzz seconds before the big waves arrive. Enough to stop trains, open fire station doors, even send out alerts to phones. Seconds matter, and we're finally starting to treat plate boundaries not as mysteries, but as neighbours with mood swings. And then there are the myths, human stories wrapped around tectonic realities. The idea of an Earth that shakes when angry, that lava comes from an underworld, that mountains rise from divine wars, they're not wrong in their own way. Cultures around the world have built cosmologies around earthquakes and volcanoes. The Maori speak of Ruaumoko, the god of earthquakes. In Japan, earthquakes are blamed on Namazu, a giant catfish that writhes beneath the islands. Hawaiian legends tell of Pele, the goddess of fire and volcanoes whose footsteps shape the islands. These stories are poetic translations of real experiences, of watching the ground move, the sea vanish, or fire erupt from solid rock. Plate tectonics may be science, but it's also drama, and humans have always needed to make sense of that. You kneel now beside a humble monument in Alaska, where the 1964 Good Friday earthquake struck. Magnitude 9.2, still the most powerful recorded in North America. Entire blocks of anchorage sank. Coastal land dropped meters. Tsunamis spread across the Pacific. The earth literally rang like a bell. And still, people rebuilt. Because we're stubborn and resilient and weirdly optimistic. Historians still argue whether it's smarter to abandon dangerous zones entirely or engineer better solutions. Truth is, we probably need a bit of both. Cities like Tokyo, Santiago, Jakarta, they aren't going anywhere, so we adapt, we study, we learn the rhythms of the plates below. You walk now through Reykjavik, Iceland, where geothermal pipes warm homes and hot water from a mid-ocean ridge literally fuels everyday life, where a divergent boundary cuts the island in half and people casually drive over it. This is tectonic harmony, when humans learn not just to survive on the plates, but to thrive with them. And finally, a reminder, we're not just on the plates, we're from them. Tectonics shaped the continents where we evolved. The rifts, the uplands, the coasts. They dictated where early humans moved, what we hunted, where rivers formed. Even the copper, tin, and iron that drove ancient civilizations came from plate-driven processes: volcanism, subduction, metamorphism. Our cities are wired with plate-borne metals. Our economies run on minerals gathered from fault zones. So yes, we build on dangerous ground. But that's only because there is no safe ground. Not really. The earth moves, the plates shift, and all of us, every city, every farm, every forgotten temple, are just brief visitors riding on giant rocky rafts, floating slowly across a sea of molten rock. Some of us even eat ice cream on them. The wind feels different now, not ancient or timeless, but restless, like it knows something you don't. The sky's familiar, but the world beneath it, just slightly off. The continents seem shuffled. The oceans, wider in some places, narrower in others, and the map you once knew, it's drifting into the future. Because here, in this quiet moment, you're peering into the next big shift. Tectonic plates never stop, even when we do. They crawl onward at centimetres per year, but that's enough to reshape the entire face of the planet given time. And time, as you've noticed, is something Earth has plenty of. So let's do the slow zoom out, 100 million years into the future, give or take a few rock layers. First, the Atlantic Ocean. It's still growing thanks to the slow divergence at the mid-Atlantic ridge. The Americas are inching westward, parting further from Europe and Africa. But the Pacific? It's shrinking. Subduction zones around the Ring of Fire are gobbling up the oceanic crust like a geological cleanup crew, pulling it down into the mantle one trench at a time. Eventually the Pacific could close entirely, bringing Asia and the Americas back together in a massive tectonic reunion. Some scientists call this hypothetical supercontinent Amasia. In one version, the continents collide near the North Pole, forming a new equatorial ocean. The Arctic becomes tropical. Penguins adapt or move. Another theory puts the next supercontinent in the southern hemisphere, Pangaea Proxima they call it. In this scenario, the Atlantic closes and the land masses swing back around to create something oddly familiar. A full circle moment, as if Earth just couldn't help herself from rearranging her continents into something Pangaea-shaped again. Historians still argue which model is more likely. It depends on how strong the current plate motions stay, how long subduction zones remain active, and whether new rifts open up in unpredictable places, because the future is a chess game played in basalt. Right now, there's even evidence of a nascent subduction zone off the coast of Portugal. If it becomes a major player, it could one day help close the Atlantic. That would shift the tectonic script entirely, putting Europe and the Americas back on a collision course. Nothing like a little continental déjà vu, but it's not just the continents shifting, entire oceans will vanish. The Mediterranean, for example, is already a remnant of the vanished Tethys Ocean. In 5 to 10 million years, it could close completely as Africa continues to ram into Europe. The Alps may rise higher, the seafloor will crumple into new mountain ranges, and yes, Italy's days as a boot-shaped peninsula might be numbered. Meanwhile, the East African rift is still pulling. Eventually, a chunk of East Africa could break off entirely, forming a new island continent in the Indian Ocean. Think of it as Gondwana 2.0. That process is already underway. Cracks have opened, lakes are forming, and the land is slowly pulling apart like warm taffy. You walk now across a stretch of future coastline. It's not on any current map. Maybe it's what remains of Florida, after rising seas and shifting land dragged the shoreline inland. Or maybe it's a ridge formed by new volcanic activity where a rift opened under what used to be Central Australia. Tectonics is patient but unpredictable. A quirky prediction. Some scientists think that if current trends continue, Australia will eventually collide with Southeast Asia, adding its bulk to that tangled web of island arcs and subduction zones. Goodbye, isolated island continent. Hello, tectonic traffic jam. The Himalayas, already absurdly tall, could get taller still, unless India finally slows down or the collision broadens into a more distributed zone. Either way, the world's rooftop is still under construction, and beneath it all, Earth's mantle continues to churn. Convection currents, mantle plumes, and subducting slabs. These hidden drivers will keep shaping the crust above, even as we build cities, draw borders, and pretend the ground isn't slowly inching in some new direction. You step now into a dense forest. Wait, is this Siberia? It doesn't look like it. The climate is warm, humid. The trees are tropical. Because as continents drift, climates drift with them. Continental positions affect ocean currents, wind patterns, and heat distribution. A supercontinent centered near the equator could trap heat, creating vast deserts in the interior. One centered at the poles could trigger new glaciations. The ice ages weren't one-offs, they're just a part of the cycle. And with shifting landmasses come shifting ecosystems. Plants and animals that once thrived in one region will be isolated or suddenly connected to new habitats. Evolution adapts, or doesn't. Species migrate, change, or vanish, just like they always have. You look up now at a mountain range that doesn't exist yet. Maybe it's the future Caribbean Andes, born from the slow convergence of plates in Central America. Maybe it's a second Himalayas, rising where Antarctica finally breaks free from its icy prison and drifts north to slam into Australia. Historians still debate whether Antarctica could become tropical again. After all, 50 million years ago it was warm, forested, and inhabited by freshwater creatures. If it drifts far enough north, it could be again. Ice isn't permanent, not in a world with moving plates. You kneel by a beach and find a chunk of polished basalt. It came from a mid-ocean ridge that doesn't exist anymore. It formed when magma spilled out between plates that no longer touch. A fossil of movement, proof that even oceans have lifespans. And here's the thought that lands hardest of all. The continents don't care if you remember them. The coastlines will redraw, the mountains will change names, the plates will keep drifting long after maps, languages, and even species fade. But if you could time travel forward, say 250 million years, you'd find a new world. Familiar yet alien. A single continent. A different set of seas. And maybe, just maybe, someone else, standing on a rocky outcrop wondering how it all came to be. You dust your hands, gaze at the horizon, and understand the next big shift isn't coming. It's already happening. You just can't feel it. Yet. You sit now, finally still, on a grassy hill overlooking a quiet valley. The sun warms the rocks around you, and somewhere nearby, water trickles over stones that have been shifted, tilted, and reborn more times than the landscape remembers. But you remember now. You've seen beneath the crust, you've watched the continents drift, and you've come to accept a simple, haunting truth. You're floating on a broken world, not broken in a poetic, heartsick way, broken as in literally fragmented, shattered into slabs and chunks, tectonic plates that grind, slide, crash and creep endlessly over the surface of a restless planet. And everything you know, everything you love, everything you've built, it all sits atop one of these mobile slabs, like a vast balance precariously on a moving cart. Right now, you might be on the North American plate slowly drifting westward, or the African plate moving a smidge north, or even a little microplate like the Cocos or Scotia, often overlooked but just as important in Earth's choreography. Wherever you are not still, and you never have been. Let that sink in. The ground beneath your feet is in motion, always. You don't feel it, not in a day or a year or even a lifetime, but look back across deep time and it becomes painfully clear. The Earth is never finished rearranging itself. You cast your gaze out and picture the hidden forces below. Mantle convection, that slow swirling dance of hot rock rising and cooler rock sinking. The crust rides above it like flaky pie topping on bubbling stew. Sometimes it stretches and thins, sometimes it wrinkles and folds, sometimes it cracks wide open and spills fire, and you build roads on it, cities, kingdoms. Every monument to human ingenuity is sitting on something that wasn't there 200 million years ago and won't be there 200 million years from now. The continents are passengers on massive geological rafts, and even they aren't safe. They're built on crust that gets recycled, melted, remade, uplifted, or buried depending on which way the plate is drifting. Let's talk about the edges of your world, the boundaries, those danger zones. They're where the most obvious signs of motion occur: volcanoes, earthquakes, mountains, trenches. But they're also the most creative places on Earth. Every mountain range is a love letter from two plates that couldn't get out of each other's way. Every volcano is a pressure valve for a planet trying to cool down without exploding. Every deep ocean trench is a goodbye letter. One plate surrendering its crust, slipping beneath another into the quiet furnace of the mantle. Historians still argue whether plate tectonics is unique to Earth, or if we're just lucky enough, or unlucky enough, to live on the one planet in the solar system where the crust is on a permanent field trip. But so far, Earth stands alone in this regard. Mars, Venus, Mercury, none show evidence of true plate tectonics, maybe in their pasts, maybe never. So when you look down at your feet, what you're really seeing is privilege. You're standing on a planet that moves, one that breathes through fault lines, that evolves its own surface, that refuses to be still or finished. And sometimes it reminds us, with a quake, a plume of ash, a sinkhole, a sudden, inexplicable shifting of the very ground we trust the most. But most days, it's gentle, slow, background hum, and we ignore it. We draw borders that the plates don't care about. We name continents, countries, coastlines, all on drifting crust that won't stay put. In the time it took you to read this section, your continent moved a few millimeters, not enough to notice, but enough to matter, eventually. Because that's what tectonics is. Earth's way of telling us that nothing is permanent. Not land, not oceans, not even the mountains. In deep time, everything changes. That's the rule. The continents we know will crash again, merge again, rip apart again. New oceans will form. Old ones will close. The face of the Earth will rewrite itself, one invisible inch at a time. You stand and feel it now. Not a jolt, not a quake, but a presence. The ground isn't still, it's in transition, and so are you. This world is not fixed, it's floating, it's fractured, and somehow it works. So the next time you look at a map, remember, it's a snapshot, not a truth. The Earth is drawing over it even as you trace the lines. Slowly, persistently, relentlessly. You're floating on a broken world, and it is magnificent. Not because there's nothing left to say, but because you've travelled far enough tonight to start recognising the patterns. Earth breathes in geological time, and you've ridden every inhale and exhale. But now things slow. Voices fade. The crust beneath your feet quiets its cracking rhythm, and the plates seem to move just a little more gently. You're lying on your back in a field now. The stars overhead don't care about continental drift, but the ground below you, it does, and it's still moving. But tonight we won't chase the motion anymore. Instead, we'll settle into it. Let it rock us like the old pulse of a living planet. You think back to where we began, Pangaea, that ancient supercontinent splitting apart in slow seismic sighs. You watched the crust stretch and yawn into rift valleys. You hovered over newborn oceans where lava hissed and cooled into brand new Earth. You watched continents collide with all the grace of a billion-ton traffic jam and rise into mountains that still haven't stopped growing. And beneath it all, the same engine, Earth's inner heat, rising through the mantle in patient loops, dragging continents along for the ride like driftwood on an unseen tide. You breathe in. The air is heavy with the memory of ash, sand, and seawater. Drifting continents left behind matching fossils, symmetrical magnetic stripes, and mountain ranges that once spanned connected lands. They told you where Earth had been, and whispered hints of where it's going. Through it all, the plates never rested. They spread, subducted, transformed, folded, fractured, and fused. And now, they slow. Your mind touches down again on the edge of a plate boundary. Not in alarm, but with understanding. It's no longer just a fault line. It's a conversation, one that began billions of years ago, and will continue long after your own story fades. The ground beneath you isn't solid. It's responsive. A record. A rhythm. A reminder that stability is temporary, and motion is eternal. You close your eyes. Somewhere a volcano smoulders beneath a sleeping mountain. Somewhere else a microplate is crushed and swallowed. And far beneath it all, the mantle exhales heat into the base of the crust, whispering to the plates above, "Keep going, keep moving. You feel no danger here, just a slow, ancestral calm, the kind that hums through rock, not blood. The Earth will change again. The continents will regroup. The mountains will sink. The oceans will realign. But for now, just for now, everything is drifting at exactly the speed it should. And so are you.